So this is the second installment on generalized quantifier theory. So what we did in the previous module, we saw what was new about generalized quantifiers. We also saw how you can extend quantification theory that was derived from systems based on first order logic. Now in this module, what we will do is we will consider the matter of the semantic interpretation, the compositional semantic interpretation of sentences that involve multiple generalized quantifiers corresponding to noun phrases. Okay? So the system that we had previously allowed us only to interpret allowed noun phrases that express generalized quantifiers that were in the subject position. What do we do when the noun phrase appears in the object position? What happens when a sentence contains more than one quantified noun phrase? To see this, consider the following sentence: exactly half the boys kissed some girl. Now, example of this type involve what is called scope ambiguity. This sentence is ambiguous even though the ambiguity is neither the result of lexical ambiguity nor the result of surface syntactic ambiguity. In both interpretations, kiss is the main transitive verb, exactly half the boys is the subject of the sentence, some girl is the object. To see that this sentence is indeed ambiguous, note first the following two interpretations corresponding to this sentence that can be described as follows. Exactly half the boys kissed some girl or other. This would be true in a situation where the number of girls, the number of boys who kissed some girl or other is exactly half of the boys overall. The other half didn't kiss any girl. There is a second interpretation of this sentence that says there is some girl, say Fatima, whom exactly half the boys kissed. Both interpretations are possible. They can be disambiguated by the prosody and so on, but you should see that both interpretations are in principle possible. The interesting thing about this pair of examples is that the two interpretations are logically independent. That is, neither entails the other. So in other words, it is possible for 2A to be true in a situation and 2B false, and for 2B to be true in a situation and 2A false. To see this, consider two situations M1 and M2. In M1, we have four boys: Aaron, Brad, Chris, and Dominique, and four girls: Alyssa, Fatima, Georgina, and Harriet. Aaron kissed Alyssa, Brad kissed Fatima, Chris and Dominique didn't kiss anyone. In M2, 2A is true, but 2B is false, since there is no girl whom exactly half the boys kissed. In M2, we have the same boys and the same girls, but Aaron and Brad kissed Fatima, Chris kissed Harriet, Dominique didn't kiss anyone. In M2, 2B is true, since there is one girl, namely Fatima, who was kissed by exactly half the boys. But there are three boys who are girl kissers, hence more than half the boys, making 2A false. How then are we to account for the two interpretations of the sentence? What this means is you can't reduce one interpretation of the sentence to another interpretation, and so on. So you need to have an account that gives both of these interpretations differently. Now, there are two broad families of approaches that attempt to account for scope ambiguity. One assumes that the rules of semantic composition must be formulated in such a way as to make it possible to assign more than one interpretations to sentences that contain more than one NP. There are various ways of doing this. There is no one account in this general family of approaches. But the basic idea that they all share is that you assign more than one interpretation to sentences that contain more than one NP. Another approach assumes that one must assume that rules of semantic composition that apply are simple ones that we basically know from first order logic and from the extension to generalized quantifier theory that we saw in the last chapter. Okay, but in order for this system to work, the rules of semantic composition must apply not to the surface syntax, but rather to a level of more abstract syntax. This level of abstract syntax in current linguistic theories is often called logical form, uppercase F, L, uppercase F, LF. We will follow a version of the latter approach as it allows us to keep a relatively simple semantic theory, though it complicates the syntax somewhat. So what do? We assume, following the principles, following the proposals of the linguist Robert May, that noun phrases can move at a level of abstract syntax, leaving co-indexed traces, just as overt syntactic movement does in languages that have them. So, for example, WH movement in languages like English and many other languages. The only difference is that whereas overt movement is visible to the phonology, this kind of covert movement is only visible to the semantics and not to the phonology. Now, once we assume this, what do we have? It is possible to assign more than one abstract syntactic representation at logical form to the sentence corresponding to the one that we started with. Okay, exactly half the boys kissed her. Some girl. One is one where you have exactly moves all the way up, carries an index 1, then some boys moves, some girl moves, carries an index 2, and it leaves traces that basically say T1 kissed T2. The other possible interpretation would be one where some girl has scope over exactly half the boys. So you have some girl co-indexed with 2, followed by exactly half the boys co-indexed with 1, and then you have T1 kissed T2. Now, in general, any sentence, n noun phrases can in principle have up to n factorial logical forms. Okay? Now, as is customary in semantic theory, structures are interpreted relative to models, which consist of a universal discourse and a valuation function, which assigns values to lexical items of a language. Okay? In this module, we won't look at pronouns and just stick to traces. Traces get interpreted as variables. Predicates are interpreted the way we are familiar with already. Proper names are interpreted, again, the way we are familiar with already. Truth is defined relative to a model and an assignment function G, and then relative to M. So these are things we have already seen when we dealt with first order logic and so on. Semantic relationships like entailment, logical equivalence, etc. are then defined by generalizing over models. So what would the rules of semantic composition look like? In this system, we assume that a model is an ordered pair of a universe of discourse and a valuation function, that assigns values to lexical items constrained by the grammar. Okay, so transitive verbs are assigned sets of ordered pairs. Intransitive verbs and common nouns are assigned sets of members of you. Proper names are assigned members of you, and determiners are assigned functions from sets of members of you to sets of members of you. Basically, this is something that we already saw in the previous module. So the semantic value of boys in a model M will be the set of all x's from my universe of discourse such that x is a boy in M. Similarly for girl, kiss will be the set of ordered pairs of x, y such that x is in U, y is in U, and x kissed y in U, and so on. Okay, sings will be the set of x's in U such that x sings in M. Exactly half the is a function which, when it applies to a set A, gives you the set of all b's that are subsets of U such that the cardinality of A intersection B equals the cardinality of A minus B. Okay, where A is also a subset of my universe of discourse. Similarly for sum is a function that, when applied to A, will give you the set of B's that are subsets of U such that the cardinality of A intersection B is not 0. Every most operate similarly. What are our other rules of semantic composition? We can see this in 5. If beta is a lexical item, the semantic value of beta with respect to mg is whatever the valuation function v assigns to beta. Beta is a trace or a pronoun. The semantic value of beta with respect to m and g is whatever g assigns to beta. A VP that dominates V and P gets the value, the set of all x's such that the ordered pair consisting of x and the semantic value of noun phrase of NP with respect to mg is a member of the transitive verb with respect to mg. If an S dominates NP-VP, that's 1 if and only if the semantic value of the noun phrase with respect to mg is a member of the semantic value of the VP with respect to mg. If I have a moved noun phrase, a noun phrase that has been moved at logical form, bearing the index I, then NPI S bar, when dominated by another S bar, is true if and only if the set of all x's such that the semantic value of S bar evaluated relative to M and something that we call a modified assignment function, which I will just explain in a second, G x slash t sub 1 equals 1, we form this set, is a member of the semantic value of the noun phrase mg. Now what's the notation? What does the notation g of x slash t sub I mean? Here we use the notion of what's called a modified assignment function. A modified assignment function g followed by x slash e sub I is defined as that assignment function that is exactly like g, except possibly in what it assigns to the trace e sub 1 in the following way: g of x slash e sub 1, when it applies to e sub 1, gives you x. For all y that is not e sub 1, gx slash E sub 1 assigns to y whatever g assigns to y. So gx slash e sub 1 is an assignment function that's exactly like g, okay, except possibly in what it assigns to e sub I, and it has to assign x to e sub I. Now, once we have this, you can see, and you can do this as an exercise, or leave this as an exercise. You can convince yourself that these rules do exactly what you want them to do. In fact, they you will see that they give you exactly the right truth conditions for the statements that contain for the logical forms that contain more than one logical form. So you can easily get two different interpretations for these sentences. Okay. Now, once we have all this interpretation system, various logical notions can now be defined as follows. A logical form LF, delta is said to be true in a model N if and only if delta is true in N. Delta entails omega if and only if every model in which delta is true, omega is true as well. Delta and omega are logically equivalent if and only if they are true in exactly the same models. Delta is valid if and only if it is true in all models. Delta is contradictory if and only if it is false in all models. Okay. Now, you can do some exercises. So, one of the things that you could try this as an exercise. Look at the models M1 and M2 that I discussed earlier when I introduced the point about the two possible interpretations of sentences that contain quantified noun phrases, and they have the same universe, okay, they have different valuation functions, and depending on what the valuation functions, just see that the rules of semantic composition, in fact, give you the results that we intuitively saw you must have. So in M1, one of the interpretations is true and the other one false. In M2, the other one is true and the first one is false. Okay. This is, in general, how you deal semantically with sentences that contain more than one quantified noun phrase. Okay. Now, is there more to say about? So far, we have seen. We started with quantified expressions like noun phrases that contain the determiners every and some, and then we went on to look at various things. Now, are there properties? Are there universal properties? Now, what we have done once we introduced the perspective on generalized quantifiers, right? We are looking now at what we call semantic determinants. These are expressions like every, some, more than half, and so on. Remember, semantic determinants don't have to be determiners in a syntactic sense. Okay? They could just be something more. They could be syntactically complex. Now, there are lots of things that could be possible semantic determinants. Now, the way we are looking at it, a semantic determiner is any relation between the extensions of two predicates. And depending on how you look at it, you can look at it as a second order predicate of two concepts following Frege, or in our terms, you could take semantic determiners as expressing relations between two sets. Okay. Now, there are all kinds of relations between two sets. Are there any constraints on what kind of relations are the ones that you expect to find in natural language. Can any arbitrary relation between two sets be a semantic determiner in a natural language? Are there any constraints on what these on what your semantic determiner could be like? Now, there have been some proposals in this direction given by people like, this comes from the work of many people, both logicians and linguists, who have in fact proposed that there are some constraints, or at least there is at least one constraint on the kinds of semantic determiners you would expect in natural language. That's number one. Number two, it turns out that even though that there are some properties which, even though they are not universal that are not universal in the sense that not all semantic determiners are constrained in this fashion, it turns out that some properties on the denotations of semantic determiners, in fact, has linguistic relevance. That means if a determiner has a certain property P, then it will behave in a certain way in natural language. So we will take a look at various examples of something like this. Okay. So let's start looking at the first such a universal. Now, one such constraint is called the semantic universal of, this is the constraint that we call conservativity. A determiner D is said to be conservative, is said to have the property cons, if and only if D A's or B's is true, if and only if D A's are A's that are also B's. Okay, that means DAB equals DA A intersection B. What does this mean? This means that if you want to see whether a statement of the form DA's or B's is true or not, you don't need to look at everything that is in B. All you need to worry about are things that are in both A and B. Okay? So if B is your second argument, you don't have to look at everything that's in B. Just look at those things that are in A that are also in B. Okay? Now, what does, in practical terms, what does this mean? This means is that every semantic determiner in natural language has to have the property that if DA's or B's is true if and only if DA's are A's that are B's. So look at the statements. Every student came to the party. You can show, you can convince yourself that it's logically equivalent to every student is a student who came to the party. Some student came to the party is logically equivalent to some student is a student who came to the party. At least n students came to the party is logically equivalent to at least n students or students who came to the party, and so on. You can convince yourself it's true of most, it's true of many, it's true of at most n, it's true of few n, it's true of a few n, what have you. Okay. Now, one can multiply examples to, if you want to see this mathematically, let's look at, now, what would it mean for a hypothetical determiner to violate conservativity? To see this, consider a determiner meaning that is not a hypothetical determiner meaning that's not conservative. Okay, let's say we take a look at the example 16. D1 A's or B's if and only if B is a subset of A. Okay, so this is in some ways the opposite of every, right? So every A's or B's is true if and only if A is a subset of B. This is one that says D1 A's or B's if and only if B is a subset of A. Now, to see that D1 does not satisfy cons, you simply note that D1A, A intersection B, by the definition 16 is true if and only if A intersection B is a subset of A. Okay? But A intersection B is a subset of A is a tautology, and therefore is always true no matter what. But 16 is a contingent state. Okay? 16 could be true or false depending on what A's or B's are. But D1A, A intersection B is always true no matter what. Okay? Now, what does this mean? Well, in fact, there is one natural language expression that looks suspiciously like D sub 1. And that's, if you think about it, the word only in English and its counterparts in other languages to a first approximation, at least when they combine with something nominal in a noun phrase, have a semantics that can be approximately given by what you see in 16. Now, does this mean that the existence of only falsifies the conservativity universal? Not quite. It turns out that only is not a true determiner, though it suspiciously looks like one in sentences like only students are allowed in this hall. One can see this by just look at the distribution of only. Okay? It is true that you can say things like only students are allowed in this hall, but only can appear in all sorts of different places. In fact, only is an adverb that can associate with something that's focused in a sentence. So you look at sentences in 17, John only sang, focus on sang. John only sang sonatas, focus on sonatas. Only the virtuous shall enter the kingdom of heaven. Okay? Now, so 17, A, B, and C very clearly shows that only is not a determiner, right? Because you have an example where only appears attached to a full noun phrase or determinant phrase, depending on how you look at it. Okay. It's only is just an adverb that attaches to the end. It's not like only combines, so only is not a semantic determiner, because in that noun phrase, the semantic determiner is the, and we know that you can't have more than one semantic determiner in a noun phrase. Now, you can also construct other hypothetical determiners that violate conservativity. So one such example, which is due to the linguist Richard Larson, says basically null A's or B's if and only if U minus A is a subset of B. Okay, what would that mean? Well, if such a determiner null were to exist, null squares are striped would mean something like everything that is not a square is striped. And it's easy to check that null also doesn't satisfy the conservativity condition. You can very easily check this in a model in which the universe consists of A, B, C, D. A consists of A, B, B consists of A, C, D. Here, U minus A is C, D, and so U minus A is a subset of B, but AB equals A, and so U minus A is not a subset of A intersection B. Okay? So this means that null AB is true in 19, but null A intersection B is not. Determiners like null simply do not exist in natural language.